magnitude of electrical force between two charges. And we could probably derive this, at least at the conceptual level. So let's say, for example, I have a sphere of charge that has 1, 2, 3, 4 extra protons. Let's say I have another sphere that has 1, 2 extra electrons. Okay, so these are going to be attracted, right? Opposites, positive, negative, are going to be attracted. So what are some factors that you think might affect how strongly they're attracted to each other? Distance. Good, so the distance. So for example, if I were to move this sphere back over here, what do you think would happen to the force? It would decrease. Yeah, the farther you are. And you saw this in the demo that I did. As I moved closer, it started to become more attracted, right? And so the closer you are, the stronger the attraction would be, or repulsion. So anyways, this is a direct or an inverse relationship. As the distance increases, what would happen to the force? Decrease. So that's called an inverse relationship. So mathematically, when we do this, so we'll write F equals, where do we put inverse relationships? In the numerator or denominator? Denominator, right? So we'll just call this D. Okay, any other factors you can think of? Yeah.
How strongly one's charged compared to the other?
Good. The amount of charge that these might have. So for example, if instead of having 1, 2, 3, 4 protons, maybe I give it 5, 6, 7, 8 protons. What should happen to the force? Should increase. Yeah, there's more positives here. They're going to more strongly attract the negative over here. Okay? So if the charge goes up, what should happen to the force? Should also go up. And this is true on both sides. So the symbol we use for charge is Q. So since there's two Q's, we're going to put Q1 and Q2. So yeah, let's just label what these mean. So Q is the charge. Can you remember, anyone remember the unit for charge? Coulomb. Okay, so that's where we get that name from this guy. So that's going to be charge. And if it was just one electron, what would be the charge?
Negative
1.6 times 10 to the negative 19, right? And so depending on how many you have or how many extras, or sometimes they'll just tell you what all the whole value is for Q. Okay, and then D is the distance between okay. Now I'm going to fix this equation because this is just the conceptual relationship. As it turns out, this is not simply D, but D squared. There's also another, what we call a constant, proportionality constant, which we're going to call K. K is just a constant, Coulomb's law constant, that's what we call it. This is easy number to remember, 9 times 10 to the 9th. The units, well, the purpose is to get to a Newton for the unit, so this would be newtons meters squared per coulomb squared. This should look familiar. What does this remind you of? The gravity equation. Yeah, identical really to the gravity equation, at least in how it looks. What was the gravity equation? Big G mass over d squared, right? Yes?
Why isn't the mass a factor? Like when you did the balloon experiment yesterday, the pieces of paper flew up, but like the whole desk or something.
So in terms of the attraction, the force of attraction, mass is not a factor in electrical force. It would be in gravitational force, as we just said. So this is just electrical force. Now, why do you guys think the paper flew up, but not the desk?
The force of gravity is less than 4.
Okay, so the paper, so here's our balloon, right? Negative, 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 negative. The paper has a very small force of gravity, right? So maybe its weight is only like 1 Newton, which it's probably way less than that. But let's say it's small. Well, the desk is maybe like 1,000 newtons, right? And so it has to, the force of electric force has to be strong enough to overcome that one. It just has to be 1 Newton to overcome it. It has to be 1,000 newtons to pull up the desk. By the way, going back to the lightning, conceivably, let's say this is your cloud. Instead of lightning, what could happen?
Float up.
Okay, you levitate, right? Or you float up towards the cloud, up and away. However, your weight is too heavy, it's too strong, and so lightning happens before you float away. Okay, all right, let's do an example.
So like if a baby was crawling out the would it be
Still not strong enough.
Oh, okay.
The baby would probably die.
Falling out of the airplane.
What about the airplane?
Yeah, into a thunderstorm. It fell out of the airplane. Would it be enough then? Just like suspend itself inside the thunderstorm?
Like if you jumped out.
It's already.
I don't know. I don't think anyone's done the experiment, so.
Not
Okay.
like with the airplane, just like.
Or would the airplane use less fuel then because it'd be polarized in the middle, so you could just float.
Okay, so let's keep going. So let's try this problem. Okay, so we said this was 1, 2, 3, 4, 5, 6, 7, 8, right? 8 protons. And we said this was 2 electrons. And let me just give you a distance here. Let's say we'll just use a nice 10 centimeters. So let's just do a quick calculation and find out the force between the two. So we're going to use Coulomb's law equation. Before we do that, though, we need to find the charge on each. So let's call this Q1, we'll call this Q2. So how are we going to find Q1?
8 times 1.6.
Okay, good. So there's 8 extra protons. So we're going to multiply 8 times the charge on 1 proton, which is 1.6 times 10 to the negative 19. And that'll give us the charge over there. .28. So the units here are coulombs. Make sure that you, when you're looking at the problem, you're not, when they give you a number, sometimes they just give you this. They tell you the charge. So look at the units. You don't always multiply by this, only if they tell you how many extra electrons or protons. Okay, go ahead and do Q2. What are we going to do for Q2? 2. So 2 times 1.6. So let's go ahead and find the force now. So we're just going to use our equation, KQ1, Q2, D squared. What do we have to do at 10 centimeters? We do it before we square it, yeah. Change it to meters first, and then square it. So make sure you're capable of plugging this into your calculator. That's some of the biggest mistakes, are simply not calculating it right. Remember the little e secret, 1.28 e to the negative 18.
So for both electrons and protons, where in this case, like you don't write the negative 2 times 1.6. It's always positive. Like.
Yeah, so that's a great question, and
It's like an
you should
absolute-
always make it positive. Yeah,
like an
always
absolute
make it positive.
value.
Right. So I would always make it positive, and then in the end figure out direction. Because remember, positive, negative means direction when, in terms of forces.
Yeah, yeah.
What's the answer you're getting for this? It's probably a really small number, right? 2.69?
Yeah, 2.69 for each of the
Negative 23? Okay, good, confirmed. So notice it's a very weak force, and the reason is we only had 8 protons and 2 electrons. When you have such small amounts, not much is going to happen. When in the last problem, or the warm-up, we had like 23, 10 to the 23rd, then big things happen.
Mr. President,
Yeah.
we got 3.6864 times 10 to the negative 25th.
And 45 times 3
You wrote 2, I said 3.
Okay, 369.